Those, when you observe those, you do change them into something new, right? And then we had physical changes and chemical changes. So again, a physical change is where somehow you alter it without making it something new. So you change the state, you change the shape, you change the size, things like that. Versus, like I said, a chemical change, you actually turn it into something new, right? So you burn it, or it's very corrosive, or reacts with acid or whatever. You make something new. And then I gave you all the evidence of ways to tell if it was a chemical change, right? So bubbles and fizzes, gives off heat, yada, yada, yada. Okay. And we talked about there are three common states: solid, liquid, and gas. Okay, so I want to draw a little triangle here on the board just to kind of highlight what the changes between the three different states are called. So I'm going to put solid on the bottom left corner and liquid over here on the bottom right corner and gas here at the top of our triangle. So when you go from a solid to a liquid, go ahead and just draw my little arrows here first. So solid to a liquid, of course, everybody knows that's called melting, right? Something, right? So solid water goes to liquid water. That's okay. That's called melting. Okay, make this marker on without making my hands entirely black would be helpful. Okay, so this is called melting. And I'm sure you all know what's the reverse of melting when a liquid goes to a solid. Freezing, yes, of course, freezing. Okay, perfect. Now, when a liquid goes to gas, that occurs at the boiling point, that process, you either hear it called evaporation or you may hear it called vaporization. Same thing. So liquid going to a gas is vaporization, right? That occurs at the boiling point. And the reverse of that, when a gas goes back to a liquid, that's called condensation. So when you have like a really cold drink and those little beads of sweat are forming on your glass or whatever, not your glass, right? That's condensation. It was gaseous water in the air turning back to liquid water on that cold surface. That's condensation. Okay? I'm going to skip this, come right back to it, and then solid to gas. Now that's a weird one. So imagine this: you have a solid, and it just skips the liquid and goes directly to gas. Okay, that's called sublimation. Sublimation. Anybody know an example of sublimation? There's one that's like really common substance that'll do this here. Dry ice, right? Yeah, dry ice is a big one. I'm sure you've all seen that before at a Halloween party or something. A big block of dry ice, and you put it there, in your punch bowl, and it goes from white solid to white smoke, right? You've probably seen that. Yeah, so that's directly to gas. Do not pass liquid. Do not pass go. Just goes directly to gas. What's the reverse of that called? Well, you can already see it up there, but the reverse of that is also a rare one. That's called deposition. So kind of the root word there is deposit. Now, an example of that is like frost. Okay, so it's maybe like, it's someday in January. It's a little cool outside in the morning. You go outside and your grass is all kind of white, right? It has that white frost on it. Maybe not here in San Diego so much, but back in the Midwest where I grew up, lots of frost and things like that. So that's an example of the water vapor turning directly to water solid on your grass, like frost. Another place where frost happens is in your freezer. So you pull out, like some meat or a fruit that's all covered in ice, right? So that was deposition. So water vapor went to water solid. It wasn't like it was water, gas, and then the fruit got really wet, turned to liquid. It just went directly to a solid. So that's called deposition. Okay, let me go back here now. So let me talk about a heating curve. I like heating curves, kind of interesting. Got all kinds of little fun little applications for heating curves. So I'm just going to go ahead and draw it again on the board, the one that's already here on the PowerPoint. Just kind of talk about it. So the way it's laid out, just going to roll up here easy. Is we're going to put temperature over here on the y-axis. And over here on the y, on the x, we're going to put the heat being added. Okay? So, let's just use water for an example, okay? So let's say I started out with a block of ice and it's really cold. Let's say it's at negative 20 degrees Celsius. Okay, so I'm starting right here with my ice. So I begin to add heat into my ice. So I add in heat and it does get warmer. It goes negative 19, negative 18, etc., etc., etc. But it's not melting yet, right? It's getting warmer until I hit what? The melting point, 0 degrees, right? So once I get to 0 degrees Celsius, so it goes warmer, 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 until I hit the melting point. Then at that point, remember I told you all the little water molecules are all locked into place, right? Remember they're all locked into place, and all they're doing at first is just what?
Vibrating.
Yeah, kind of vibrating, right? They're not actually moving relative to each other. Well, at this point, so now they're vibrating faster and faster and faster, and now they have enough energy then, at 0 degrees, they can actually break free and begin to move past each other and go to a liquid. So that's the point where they have enough average kinetic energy to actually break free and begin to, move past each other at that point. So, while they are breaking free, it stops going up in temperature. So you're still adding in energy, but all that energy is going into breaking them apart and letting them start moving freely. So the interesting thing is, while it's melting, it stays at 0 degrees. So it stays at 0. So they're melting, they're melting, they're melting, they're melting. Once they're all melted, then it starts going back up. So now they're all liquid. Now it starts going up. So you get a liquid, warmer liquid, warmer liquid, warmer liquid, warmer liquid, until we hit the boiling point, 100 degrees. So the boiling point, well, again, there is still some kind of little bit of a loose force between these, holding them together, right, as a liquid. But now in the gas phase, there's pretty much no force, right? So they're just totally free for all everywhere. So now at this point, they're moving faster and faster and faster, and now they have the energy just to totally snap every last connection, fly apart into the gas phase. So while they're breaking apart and flying off in the gas phase, same thing. You're still dumping in heat, but it's going into breaking them apart, and it stays flat. Stays flat, stays flat, stays flat, until they're all broken apart, they all have boiled, and then you have a gas at that point. So, that's a very interesting thing, I think. Let me talk about that here for a second. So here we have our freezing point, right? This is our freezing point, right? And up here we have our boiling point. All right? So we had solid was down here, right? And then here we had liquid up here in this region. Then we have gas up here in this region, right? So that means then, let's say you're at home and you're boiling water, right? You're trying to make some pasta or whatever. Well, once the water is boiling, it boils at 100 degrees. You can turn that stove up as hot as you want. You can get out a butane torch, doesn't matter. It will not boil hotter than 100 degrees. As long as water is boiling, it will boil at 100 degrees, right? So like I said, you can crank it up super hot, use whatever sort of heat you want to. It's not going to boil any hotter than 100 degrees because it stays constant while it's boiling. Are you with me? So that's called the heating curve. Now the reverse of that is just the cooling curve. Just the same thing, but just in reverse. So now though, then if you're cooling things off, well, now they're losing heat. So they're moving fast, and they start to slow down, and now they're slow enough they can actually reconnect. While they're reconnecting back as a liquid, it stays at 100 degrees. And then once they're all back to a liquid, then that liquid cools off, moves slower and slower until they begin to all lock into place. And while they're all locking into place again, it stays constant at 0 degrees. And once they're all frozen again, then that goes slower and slower and slower. That kind of makes sense how that works? Now there are some pretty cool little applications for this. I remember like in the past I used to live in Fresno the previous 3 years and tried to move down here. There's all kinds of orchards and farms and vineyards all around the area there. And one of the things you would notice that would happen is the forecast is going to call for frost, let's say one night, it's going to be really, really cold, they knew that night, right? So you would notice out in the orchards for the oranges, let's say, or for the strawberries, whatever it was, all of a sudden then, all these sprinklers would appear. They would just start spraying all their crops with water. You used to always wonder, okay, so what's going on? So they know it's going to freeze. Why are they spraying water on their crops when you know it's going to freeze? Do they want their crops to freeze? That doesn't make any sense. And actually, yes, they do want their crops to freeze. So they're spraying water, right, all over their crops. Okay, let's think about that. Okay, so let's say it's daytime still, and they start spraying water all over their orchards, their oranges, their raspberries, whatever they have. And let's say right now it's only, I don't know, it's right here. Okay, so it's 10 degrees during the day. So they're spraying water, and the water on the outside of those oranges, what's it do? It cools off, it cools off, it cools off. Well, the farmers are smart, and they know that the danger zone for most fruits is they don't want to get a fruit down to about -2. Once it gets to -2, then you begin to kill off whatever the fruit is. Okay, so their goal, like I said, is to not get to -2. Like I said, so that water, so it cools off, during the day, and then it gets to night, and now it falls to 0 degrees. Well, the water begins to freeze on the outside of the oranges, right, or the strawberries, or whatever it is. Well, while it's freezing, what happens? It stays at 0 degrees Celsius. Now, the outside air may go colder, -1, -2, -5, -10. But as long as there's still water freezing on the outside of that fruit, it stays at 0. Isn't that clever? So they just keep spraying water all night long. So they keep spraying water. They keep spraying water. If they ever stop spraying the water, well, then it would freeze, and then it would go below 0. But as long as there's still water freezing, it keeps it at 0 and never hits the -2 danger zone. Oh, those smart farmers. They know their chemistry. It's good for them. Yeah. And the other cool thing then that happens is, like I said, so this way when you're going in, right, you're having to add in heat. So now when a liquid's going back to a solid, it is doing what? It's releasing, it's losing heat. So imagine that. So now we have these oranges, strawberries, or whatever we have, and they're all covered in water. And then as the water is freezing, it's actually releasing heat into the fruit. It's actually warming the fruit while staying at 0 degrees. Isn't that clever? I thought that was really cool. So anyway, so yeah, that's the cooling curve, is just the reverse. So, okay. Learn something new. Go home and wow your family and friends. Okay. I don't know why the one's in there twice. Okay, so yeah, and here's the little thing I already drew for you, right? So that's all the 6 changes of state, and there are different names I'd be familiar with. Okay. Well, let's look at some ways we can begin to predict and measure the amount of heat that's going to be lost for something, okay? Well, every substance has a different what's called specific heat. So water, copper, iron, whatever you can think of, any substance has a unique specific heat to it, okay? So that is basically how much energy do I have to dump into this substance to heat 1 gram of it up by 1 degree Celsius. So how much heat do I have to pour into this sucker to make it increase, take 1 gram of it and heat it up 1 degree Celsius? Now that might sound kind of familiar to a thing we discussed the last time called the calorie. Because remember I said 1 calorie was the amount of energy it takes to raise 1 gram of water 1 degree Celsius. Remember me saying that? Well, if not, then I have a reminder. All right. So 1 calorie is the amount of energy it takes to raise 1 gram of water 1 degree Celsius. And we said 1 calorie is the same as 4.184 joules. Okay. So there's a little formula we can write that looks like this. The specific heat equals the heat divided by the mass divided by the change in temperature. This marker is dead. Try another one. So the specific heat equals the heat divided by the mass times the delta T, which is the change in the temperature. So it's a quick little side note. Whenever you see this triangle, that's actually, it's a capital Greek letter delta. That means the change in whatever's after it. So in this case, that means change in temperature. If it was delta P, it'd be change in pressure. Delta V would be change in volume. Okay, it's the change in whatever that is right there. Okay? Now you may also see this written out as like a set of variables. I'm going to get some better markers here. So oftentimes you might see it written as specific heat. They will call it C, because it is oftentimes called the specific heat capacity. They call it C. Heat is a lowercase q, M is for mass, and then you might see delta T still. So I'm saying you may see it also written that way, where Q is heat, C is specific heat capacity, M is mass, then delta T is still delta T. Okay, another little FYI note. When it says change in temperature, which way do you change it? Going up or going down? Well, we always consider that to be the final temperature minus the initial. So take wherever the final temperature was. So it went from 50 to 100. So it's 100 minus 50, not 50 minus 100, whatever it was. It's always final minus initial. So make a little note to yourself. And again, the same for any delta, whatever. It's delta pressure, final minus initial pressure. Delta volume, final minus initial. Okay, so this will give me units of heat, like joules or calories, over grams times Celsius, right? So in the SI system, it'll be joules per gram Celsius. In the metric, it'll be calories per gram Celsius. That makes sense, because this will be joules or calories, this will be grams, this will be change in temperature Celsius. Okay, I'm going to pause a second, let you finish writing. Then I want to show you a big table of a bunch of these, and we'll discuss why we give a crap. And maybe you still won't give a crap, even after I tell you, but you should. Okay, so we're going to look at, so again, it's the amount of energy it takes to raise a gram a degree Celsius. So it has all of those units in there. Energy, grams, Celsius. Everything's in that little calculation there. Okay, well, here is a little chart that has a bunch of these. So here it is in joules, here it is in calories. So I'll just use joules here. So if you want to heat up a gram of aluminum, 1 degree Celsius, you got to pump in 0.897 joules, right? But if you want to heat up, let's say, a gram of gold, well, it's much easier to heat up gold, right? You only got to put in 0.129 joules to make it go up 1 degree Celsius. But notice, though, water has the highest specific heat on the list. In fact, water is one of the highest in the universe. Has a freakishly high specific heat capacity. So that means water is really hard to heat up, actually. You want to heat up water, you got to put in 4.184 joules for a single gram for a single degree change. Versus, let's say, like gold, right, 0.129, or iron, 0.452, right? Just so the gold versus water, 40 times harder to heat up gold versus water. You see what I'm saying? So it's much harder to do that. Well, why do we care, right? So why is that important to us? Well, one of the reasons that NASA scientists are always trying to find water on other planets is partially because of this thing. Because they know, like I said, water is a great absorber of heat. And it allows then for you to have a planet with a very stable temperature range. You won't get huge fluctuations in temperature. So let me draw a really crappy picture. So I'm going to draw a really bad picture. But here we go. So let's say this is Earth. Hello, Earth. Isn't that awesome? And let's say this is North America. What the heck was that? I don't know what happened there. That was not what I meant to draw, but whatever. So here's North America. Oh, look, here's Mexico and Florida. Whatever. There's North America, right? So there we are. You are here on this weird tumor on the side of California I drew. Whatever that is. Okay, but, but most of the planet is what? Water. Lots and lots of water, right? We got lots of water all around us. So let's think about this for a second. So there's this big ball of fire in the sky. It's called the sun. It's kind of like a big red fried egg, apparently. And the sun is just spitting out bazillions of joules of energy at our planet every day. I mean, just megajoules, megajoules, megajoules every day at our planet. Well, fortunately, though, we have 70% of our planet covered in water. So all of the heat just beats down on our planet, and what happens? Well, like I said, water is very hard to heat up. So most of the energy, water just absorbs it. It might go up a degree, and absorbs it again, and it goes up a degree, right? So like I said, 1 gram takes 4.184 joules to go a degree. We've got bazillions of grams, right, of water. So that means that our highs and lows, that means then that our high and low change of temperature are pretty, are very narrow range for our planet, let's say. Because I'll give you an example of that. So let's say you travel out here, and you go out here into the desert. Okay, so we're out in the desert, and there's not much water around the desert, right? Okay, so there the sun beats down on you, on you, and you do get a big temperature spike, right? It goes 120, 130 during the day. And then at night, what happens? You freeze your butt off, it goes to negative something, right? It gets just the opposite. But then here in San Diego, we have lots of ocean all around us. What happens to us? Same sun, goes up a little bit during the day, goes up a little bit during the day, and down a little bit during the night, right? So it's a much smaller range. Does that make sense? It's like I said, a desert and a water. Well, because again, like I said, the water, like I said, so the water, so again, the water is absorbing the bulk of the heat that's being spit out on our planet. Versus, let's say, the moon or Mars, it'll be hundreds of degrees during the day and then negative hundreds, right, at night or whatever. It'll just be huge temperature swings there. This is also important for us as people. So I'll draw a lovely little self-portrait here. So here I am. This is me. I guess I'll give myself some hair. I'll have some hair. I have some brown hair. Brown hair. Okay, here's a little beard. Okay, there I am. And I'll get and some eyeballs. I have brown eyes. Brown eyes. And I'm very happy to be teaching chemistry, so here's my smile. Okay, so there I am. So during the day, we have same thing, right? So I go outside in the sun, not very often apparently, though, because I'm very pasty white. And the sun beats down on me, right? Well, my body temperature internally is about 98.6 degrees Celsius, right? I'm sorry, Fahrenheit. Fahrenheit, right? Which is about 37 Celsius. Okay, well, as you know, your bodies are mostly water, right? I mean, your body knows what is it? 77% water, right? You're mostly big bags of water with some other stuff floating around in it. So, it's the same thing as the planet. That sun just beats down on you, spits out the radiation and all the energy on you, and what happens? Was your temperature, does it spike up to 40 degrees all of a sudden you go outside? No, it stays around 37, right? Why? The water is absorbing most of the heat, right? And the vice versa, right? The vice versa as well. So you go out somewhere it's really cold, you don't just suddenly drop down to 95 degree in current right temperature inside. Okay, so let's just do a little quick and dirty math. So again, if you want to heat up 1 gram of water, 1 degree Celsius, it takes 1 calorie, right, to do that. So let's say so yeah, let's say then you're a little sick and you have a fever of just 39 degrees because you have a 2-degree fever, so you go into the hospital. Why is a 2-degree fever such a big deal? Okay, so let's think about that. So let's say an average person weighs about 70 kilograms. Okay. Well, how many grams is that? Well, 1 kilogram is 1,000 or 10 to the third grams, right? That's a really crappy G, sorry. So that's 70,000 grams. Are you with me? So, okay, this is, okay, again, like I said, you're mostly water, you're not all water, but I'll just assume you're all water, okay, just make it easy math. So, if you were really 70,000 grams of water, and you had a fever of just 2 degrees, okay, well, to heat up 70,000 grams of water 1 degrees would take 70,000 calories, right? And to heat up 70,000 grams 2 degrees is going to take 140,000 calories, right? So that means that your body is spitting out an extra 140,000 calories of energy it's burning up. So they're like, what is going on with your body? Right? So that's like a small fever. I mean, it really is, right? It's an insane amount of extra energy being produced by your body for some reason. Does that make sense? Can you see why that's so important for, like I said, water is so important? Versus, let's say you went outside and you were a robot. Okay? So you go outside. Here I am. I'm a little robot now. I'm a robot. I'm a little robot. Whatever. Okay. And now I'm made of iron, and so the same thing happens, right? The sun beats down on me. Well, now what happens into me? Because let's say, the robot is 37 degrees too to start with. He goes outside, and the sun beats down on him. Well, he will not stay at 37 degrees very long, right? Because the iron, or whatever you're made out of, right, it absorbs heat 10 times or 40 times worse, right? So it goes up 10 times faster. So you would go outside and you would suddenly spike a big fever up to 47 or 57, whatever it was, right? And you can go outside in the sun. And then if you go outside somewhere then that's really cold, you're going to freeze and you'll just drop down to 35, 27, or whatever. Does that make sense? Okay. Fascinating. I can tell you're thrilled. But yeah, like I said, so if you're iron, right, compared to water, it's 9 times easier to heat up iron, right, if you're a robot than it is if you're made out of water, which we are. So that is why your body temperature stays pretty constant, as well as our planet's temperature stays pretty constant, because of the importance of specific heat. Okay. Oh yes. So here's a funny little picture I took when I was at the University of Edinburgh a few years ago. I was visiting over there in the chemistry department, and we were meeting over there with a lady named, what's her name? Dr. Eleanor something, and she's the chair there for the chemistry department. And in her office, we walked in the office there, in her office, on the left-hand side, she had a big line of these old chairs on the left-hand wall. I asked her, hey, what are all these old chairs? And these are the chairs that were actually used by the previous chemistry department chairs, previous years. This is the chair's chair of Joseph Black, who's a guy that kind of so this is the chair's chair of Joseph Black, who's the guy that figured out specific heat capacity. So anyway, it's kind of funny. So here, like I said, it's an old chair from 1766, and that's where his butt was 300 years ago, or whatever it was. Right. So right there in that chair, 250 years ago. So there it is. There's his chair, the chair. So, okay, so let's just try a couple of calculations, and let's use this and see, okay, so how could I calculate then the specific heat of an unknown substance? So we're going to do a lab like this. I think it's in 2 weeks, and you're going to have an unknown metal, and you're going to heat it up, and you're going to, and based off the mass of the metal, how much the temperature changes, and how much heat it absorbs, we're going to figure out what a specific heat is. And then you can go back to this table and say, aha, it was 0.897. It must have been aluminum. Or you say, aha, it was 0.452. It must have been iron. Are you with me? So yeah, we're going to do that in a couple of weeks. So let's just do one together, and then I'll have you guys try one on your own. So let's look at this one. So what is the specific heat of a metal if 24.8 grams absorbs 65.7 calories, and the temperature rises from 20.2 up to 24.5 degrees Celsius. So, my formula is specific heat equals heat over mass times change in temperature, right? So let's plug in what we know. So Q is heat. What's my heat? Which of those numbers, there's 4 numbers, which of those is my heat? 65.7 calories, right? Because heat's going to be either calories or joules. Okay? So I'll say it again. Note to self, you didn't write that down earlier. I mentioned it like 3 times. Heat's going to be calories or joules. So if you see calories or joules, that's your heat. So let's put in on top 65.7 calories. I'm going to divide that by what's the mass? 24.8 grams, right? The mass will be something like grams, pounds, whatever it is. Now I'm going to multiply that by my delta T. So I said delta T, we always do it the final where it ended up and subtract the initial where it started. So which of those 2 temperatures is the final? 24.5. It wound up at 24.5 degrees Celsius. And it started at where? Yes, so I'm going to subtract 20.2 degrees Celsius. Okay, so real quick, I'll give you a little tip here for your sig figs. Let's do the delta T first. So what's 24.5 minus 20.2? 4.3. Now remember, when you're doing addition or you're doing subtraction, it's based off the places. So this goes to the tenths, this goes to the tenths, this can only go to the tenths. So now it's 3 sig figs divided by 3 sig figs divided by only 2, right? So yeah, that's why it's important to make that first. Because if not, you all would have probably said, oh, 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs must be 3 sig figs. But it's not. It's 3 sig figs, 3 sig figs. These make 2 sig figs, so it's 2 sig figs. You see why I had to do that first? Okay, so punch that in your calculator, and what do you get with 2 sig figs? Give me an answer.
0.62.
0.62. 0.62. Next question. What are the units? Which units are there still left that weren't canceled out or anything? There's still calories on top. There's still grams on the bottom. And there's Celsius on the bottom still, right? So that's the units. And that's the unit that we said we should have for this, right? It should be either calories per gram Celsius or joules per gram Celsius. That makes sense. That's a good unit. So units are always a good way for you to check and see if your answer makes sense. Right? So if your answer worked out, let's say calories per gram, there was no Celsius, you'd be like, oh crap, I messed up, or something like that, right? You can always kind of tell at least a little indicator based on your units. Yes?
Are we supposed to keep the original number of decimal points on the temperature?
Yes, we did. So that had a decimal, that had a decimal, so that had a...
But the answer has 2 decimals.
When you're converting between Celsius and Fahrenheit, I was saying do that. Yeah. In this case, all we're doing is just a little addition and subtraction. So that's still decimal places too. Okay, your turn. Try the next one. Try B. Hopefully you have your hand out. If not, slap yourselves. Remember for next time. And then maybe you'll bring it. So try B. What's the specific heat of silver? And it wants it in, notice it wants it in joules this time. Joules per gram Celsius. It gives you all the info. So figure it out. Help each other out. Talk it over. Okay, do you have some answers? Talk it over. What do you think? 0.237. Okay. Anybody else?
Joules over grams degrees Celsius.
Joules per gram degree Celsius. Okay. Anybody else? Anything different? Same? Same? People nodding, I guess yes means same. Okay. Okay, well, good. Well, let's try it out. See what we got. So, we want to find the specific heat, which we call C. And that's equal to Q over M times delta T. But I want the Q to be not in calories, but in joules. So I got to convert 38.5 calories into joules first, right? I'm going to do that just separately here. We know that 1 calorie is 4.184 joules, right? So you punch it in your calculator. Let's see. 38.5 times 4.184. 161.084 joules. Okay, let's figure out our sig figs real quick. How many sig figs are in 38.5? 3 sig figs. How many are in 4.184? Do you recall? That one's actually not 4. I told you that was one. That is exact. That is defined. That is exact. That is exact. So the answer has to have 3. But I told you, right, don't round until we get to the last step. So I'm going to go ahead and just kind of mark it at 3 to remind myself, but I won't round it until I get to the end. So, okay, so let's punch that in as my heat. And again, you want to keep at least 1 extra, or you keep them all. I'll just keep them all, who cares? But at least 1 extra until the end. Okay, what's my mass? 25.0 grams. Times, okay, delta T, what's the final, what's the initial? 58.7 is the final. Yeah, right. And what's the initial? 31.5. Okay, let me erase a little bit down here. So, what is 58.7 minus 31.5? I think I heard you. Right, 27.2 degrees Celsius. Okay, so you punch all that in, and now we got 3 sig figs here, 3 sig figs here, 3 sig figs here. So my answer should have 3 sig figs. So what is it? Yeah, question.
Okay, say you just, like on mine, I just went straight from like 161.084 divided by 25.0 times 27.2. Like that was my first step.
Mm-hmm.
I couldn't call that top number 5 sig figs because I would actually have to count the sig figs when you did that other conversion.
Yeah, definitely. Right. Yeah, because all those 3 sig figs here, that was exact. So that made that only 3 sig figs.
Okay.
Yeah. So I guess it's not 6. You got to count it as only 3.
Okay.
So what was it? What did you say? 0.237?
Yeah.
And now the units are, there's joules left, right? There's grams left, and there's degrees Celsius left. Okay. So notice, I just want to point out, this one was 3 sig figs. The previous was only 2 sig figs, because the previous one came out to be right like that. So yes, make sure you catch that. That'll trip you up on a quiz or a test or homework or something. So I'm warning you. Okay. Now, yes.
So if you get the sig figs wrong on the test, do you mark the whole thing wrong?
Well, it depends what it is. And if it's multiple choice, I guess you get the whole thing wrong. But otherwise, no, it's not. It's just 1 point normally for the sig figs. So yeah, you know, if you're doing a test and it's 5 points or 10 points, just 1 for the sig fig. You still get the rest of the credit. Yeah, you don't like lose everything. No. Yeah. Jen.
Just a quick question on that last one. I set my equation up completely different.
Okay.
So I just want to make sure, like, the way I set it up, I still came out with the right answer, but that's not going to come back to bite me later here.
I don't think it will.
So I just did, like, I set up the whole C equals Q over delta and T times mass first, and then I put times the...
Oh, at the end you converted it. Yeah, that'll work too. Yeah, it'll work because basically at the end what you're doing is so at the end you got calories per gram Celsius, right? And then you just got rid of the calories, so you did 1 calorie, 4.184. Yes, that still works. You still get joules over gram Celsius at the end. Yeah, so it totally still works that way too. That works, yeah.
So I got a test. Would I have to show that first conversion step?
Yes, you got to show all your work so I know where it came from. Yeah. How you got the joules, you mean? Yeah. If it always on the test, show all your work, for full credit, yeah. Also be like, where'd that number come from? You just copy it off somebody next to you? All right, so you got to show me where it came from, definitely. Okay, well, I can also rearrange this equation and solve for heat, right? So I could just move m delta T over here. I could say, oh, well, heat is mass times delta T times specific heat. So I could say, oh, well, I could also write it as Q equals m times delta T times C. So it really then would just depend on what you're trying to solve for. So if, in this case, right, you could solve for heat. Or you could rearrange it again and solve for mass. Or any other variable you wanted to. You could rearrange it, right? Just do a little algebra. Okay. So, again, if I want to know how much heat is lost or gained, well, then I got to know. Obviously, I got to know the mass, I got to know the change of temperature, and I got to know the specific heat, right? So I got to know all those things, and I can figure out. Okay. So yes, that's kind of handy. So let's say you have a big block of iron or I don't know a silver wire or whatever it is, something you're working on, and you want to heat it up 10 degrees. Well, what you could do then is you could put in 10 degrees here, put the specific heat for iron or silver, whatever it is, and then weigh it. You can calculate how many joules of heat you have to pump into that thing to warm it up 10 degrees, right? You can actually calculate how much heat do I need to heat up this metal tire rim, or to heat up, this transmission, or whatever it is, right? So the danger zone, is, I don't know, some temperature. Okay, so calculate. Okay, well, how much heat would I have to put out before it goes above that temperature, whatever. So, yeah.
Can you have negative heat?
Yes, you can have. What that means, though, it just means it was lost.
Okay.
So a negative number will mean heat is lost. Positive number just means heat was absorbed by the substance. Yes, so good question. Good question. Okay, so let's look at a couple here. Let's do at least the first couple. And I thought I made room to write on this. I guess I didn't do that yet. Okay, so you're working out and you hurt yourself. You got a really sore muscle. So you go home, you get a hot water bottle, and you heat it up, and you put it on your leg or whatever's cramping, let's say. Okay, so your water bottle contains 750 grams of water, and it's at 65 degrees. And you put, like I said, on your leg, which is hopefully at 37 degrees. So over time, it cools off down to body temperature. How much heat would have been released out of that hot water bottle into your leg if it went from 65 degrees and cooled off to 37 degrees? It tells you that the specific heat of water, or the C of water, is 1 calorie, of course we know, per gram Celsius. So, let's work that one out together. So I'm going to change a little white screen, and you can tell me what those numbers were, because I don't have it here with me. Maybe. There it goes. So, Q, let's use a smaller marker. Q equals M delta T C, right? Okay, so I want to know how many calories. So I want to know which variable is calories going to be, Q, M, delta T, or C. How many calories? Which of those represents calories? I'm solving for Q, right? Q, I said like 5 times now, is going to be like calories or joules, right? So, calories. Okay, so how many calories? So I'm solving for Q. So what was the mass of the hot water bottle? 750 grams. So I'm going to take that times the delta T. So, what was the final temperature in this case? So what was it? Which one? The final was 37, right? Because it cooled off down to your body temperature. And initially it was at 65. Was it even or was it 0.0? I can't remember. Okay, 65. Was that 65 to start with, right? And then times 1 calorie per gram Celsius, right? Water specific heat capacity. Okay, so I'm going to go ahead and solve this delta T here first. So what's 37 minus 65? Negative 28 degrees Celsius. Okay, so let's Cross out our units here. So I'm left with, calories, which I know I should be, right? Awesome. Okay. Whoops. So, try that out in your calculator. 750 times negative 28 times 1. What do you get? Negative 21,000. What's my units? What's left? Calories. Okay, how many sig figs should that have? Let's figure it out real quick. 750 has 2 sig figs. Negative 28 has 2 sig figs. How about 1? That was defined, right? Because we said a calorie has been defined to be 1. The amount of energy it takes to weigh is 1 gram, 1 gram. So this one is actually defined. So this should have 2 sig figs. So let's write this with 2 sig figs. Let's do our friend scientific notation. 10 to the 4th calories. So again, as you're just asking, can your heat be negative? It can. And again, so what does a negative 21,000 imply? It means it lost heat, right? And that makes sense, right? Because again, it was hotter and it got colder, so it had to have lost heat. Right? Everybody sees why that's negative? Okay, awesome. Nope, go back here. Okay, your turn. Try B. Try B as in Bravo. See what you get. Help each other out. Talk it over. Okay, so we had a negative 620, negative 620,000. Let's figure it out here. So you guys can give me the numbers here. So Q equals mass times delta T times C. So what's the mass?
7.40 grams.
Okay. Delta T. So what was the final temperature?
Negative 20 degrees Celsius.
No.
29 degrees.
29 degrees Celsius. And initially it was at 49 degrees Celsius. And what's the specific heat? 4.184. Okay, thank you. Joules per gram degree Celsius. Okay, let's cancel our units. Grams, grams. Oh, actually, first let's go ahead and do this right here. What's 29 minus 49? Negative 20. But I'm going to put a little decimal point here. Why am I putting in a little decimal point right there? Because 1's place minus 1's place, that 1 is actually precise. I'm going to put a little decimal to remind me. So now let's cancel out Celsius. Okay, so left with joules. That makes sense for heat. Okay. So 7.40 minus negative 20, not minus, multiplied by negative 20, multiplied by 4.184. Okay, we do a couple answers there. Negative 619.232 joules. So how many sig figs should I have though? Yeah, here's 3, here's 2, here's exact, so this should have 2, so we make it negative 620, and that's 2 sig figs, right? Or if you want to be clear, you could write negative 6.2 and just get rid of the placeholder zeros. Either way.
Would 20 be 1 sig fig though? Or you just implied that there's a decimal point there?
Well, that's what that's what I was just saying. So why did I put a decimal point there? Because I had to show it really was, that 0 actually is significant.
Okay.
Because it's 1's place minus 1's place. That 1's place isn't just a placeholder. It really is significant. So
Okay.
yeah, that's why I had to put that decimal in, I was saying. Yeah, you're right. Because if not, you would have said, 1 sig fig. And then that would have been wrong. Okay, let's try one more. Let's try the last one. How many kilojoules are needed to raise the temperature of 325 grams of water from 15 degrees to 77.0 degrees Celsius? So, try it out. Talk it over. Let's hear some answers.
840 kilojoules.
840 kilojoules. 84.1 kilojoules. 4.3 kilojoules. Well, we're all in that ballpark. 8.4 something. Okay, let's try it out. We'll work it real quick, and then we'll go over the quiz. Come on, work with me. Here we go. Okay, so Q equals M delta T C. Okay, what was the mass? 225. 325 grams. Delta T. So final minus initial. So it went from 15, I think, right? What was that? 277? So 77.0 is where it ended up at. That's the final. Minus, was it 15.0?
Yes.
Times, what was the C? 4.184 joules over grams degrees Celsius. Okay, so let's do my little delta T here first. So 77.0 minus 15.0 is 62. Don't forget the 0 though, right? Because again, tens place minus tens place is tens place. Because the calculator will not tell you to put the 0, but you got to remember, oh, I need a 0 there, right? Else you will have just lost a sig fig and get the wrong answer. So then you do all that. So 325 times 62 times 4.184. 84.3076 joules. I'm sorry, 84,000.6 joules. So that's joules, but I want to be in, it said kilojoules. So 1 kilojoule on top, 10 to the third joules on bottom, right? Now I get 84.3076 kilojoules. Sig figs real quick. The first one has 3, exact, because it's water, so 3. So it would be 84.3 joules. Kilojoules, thank you, yes, kilojoules.
Negative.
Nope, not negative. No, but it was absorbing heat. It got hotter, absorbed heat. Okay, well, good. Well, let me go over the quiz real quick. We got about 6 minutes. I just want to work a couple of them. Go ahead and pull it up here on my PowerPoint. If you can all see it together. Here on the projector, I mean. Okay, I think most everybody got 1 right. It was C. Most everybody got 2 right. The big ones that were missed were 4 was missed, quite a lot. Let me discuss 4 real quick. So we're adding, so I always encourage you to line them up when you're adding. So 2610 plus 11.7 plus 0.22. So we add them up. Get that, right? Okay, let's look at our sig figs. How many sig figs is in 2,610? Where's the last one at? In the tens place. How about this one, 11.7? 3 sig figs, last one's in the tenths place. How about 0.22? Hundredths place. So tens, tenths, or hundredths? What's the least precise? The tens, right? So I got to round it off to the tens place. So I round it off to be that one, right? So that was D. 5, quite a few of you missed 2. I was kind of surprised. I thought we kind of hammered in the it's got to be opposite kind of thing, right? So it should have been D, where the exponent's here, the prefix is here. There was only one other one that was like that, I think. Oh, no, wait, no, there's 2 like that, I think. So this one, these are opposite, but that's just the wrong number, right? Millie should be -3. This one, that's the wrong number. Micro should be -6. That's the one that had the right number and it was opposite. Okay. Let's do 7 real quick here. And then I'll do 8 real quick. So a dose of aspirin is 5 milligrams per kilogram of body weight. So that means that's a conversion. 5 milligrams of aspirin per kilogram of body weight, it tells me, right? And I have a infant that weighs 8.5 pounds. So I have 8.5 pounds of body weight, basically, right? Put 8.5 pounds body, I'll say. Well, I have pounds of body, I want kilograms, so I think it says 1 pound is 2.205 kilograms, is that what it says? Okay, so 1 pound of body, 2.205 kilograms of body. And then I'm going to use that conversion there. I need to give them 5 milligrams of aspirin.
I thought 1 kilogram equals 2.205 pounds.
Oh, is that what it is? Is that what it is? I just asked you guys. You told me the other way. Okay. Okay. Thank you for lying to me. 1 kilogram, 2.205. I'm writing messy because I'm in a hurry. Sorry. And it was 5.0 milligrams per kilogram of body. All right. And he gave you, I think it was that the one that was 19? Sorry for so messy, but you get the idea, right? So this one has to be a conversion factor, right? Because look, it says per 2 units, milligram per kilogram. It's got to be a conversion. And keep in mind, it's milligrams aspirin, kilograms body. So you can't cancel out pounds of baby with milligrams of aspirin or something, right? So you can't do that either, right? So you've got to cancel out the same thing as well, okay? We're technically out of time, so you can head out if you want. Now I'm going to work the last one real quick. Pardon me? Yeah, that's right. FLS session. Get a little hour of exciting chemistry help. I'm going to work this real quick, though, if you want to stay just for a second. What is the mass kilograms of 2.00 liters? And the density is 1.15 grams per milliliter. So I'm going to get liters into milliliters. So 1 milliliter, 10 to the negative third liters. Then it's 1.15 grams per milliliter, it said, right? That's right here. And then I don't want grams, I want kilograms. So 1 kilogram, 10 to the third grams. And then I forget what the answer was. Something 90, I forget. Like 290 or 390 or anybody know? No?
I'm sorry.
2.30. I think you're right. Yeah, 2.30 because that's have 3 sig figs. So that's that one. Okay, well, thank you. So we'll definitely finish up on Tuesday, which means after lecture is done, we'll do a little bit of some reviewing, right? But for a little extra review, go right there, Margaret. Go to FLS, and she will hook you up. Talk about all kinds of good stuff. So we'll see you Tuesday.